have seen how a strain gauge is made up of, how it is fixed in a piece, base metal, and how the strain is transduced and how to fix the strain gauges in a bridge network and so on. But now for a displacement measurement, how to use a strain gauge, that what I am explaining now. That is, now if you want to measure a displacement, give the displacement to a cantilever, for example, cantilever end, it is fixed end, this is the free end. So give the displacement at the free end, so it will deform. So by using this cantilever, what you are achieving, the displacement signal is converted into a strain signal. That is what is indicated in the signal flow diagram. This is a signal flow diagram where the cantilever is shown here, first transducer converting the displacement or transduced displacement d into epsilon strain. So afterwards, then now the strain is picked up by the strain gauge as resistance change, that will form one of the arms of a strain gauge bridge circuit. So by using the strain now, that is displacement converted into strain, this strain is converted into a resistance change which forms part of a bridge network. So now it is the whole thing is our carrier frequency amplifier. You have got oscillator giving a high frequency carrier signal, and this is our strain is our input signal, and resistance change correspondingly. You will have the output voltage EO from the bridge, and that is being amplified. This is a modulated signal. It is being amplified, and the amplified one goes to the phase sensitive demodulator, and then through low pass filter we get a voltage output. Now this voltage is calibrated, E is calibrated in terms of displacement. So you find the first what we do in this is a AC excitation. It is for AC excitation, AC current excitation for the bridge network, because oscillator gives near about 5 kilohertz frequency signal. It is used to excite the strain gauge bridge. So that is now here strain gauge bridge is all the four will be from the resistance, the pure resistances. We can either excite the bridge network by AC or DC. So this is excitation. If you use a DC excitation, it is simple circuit. Again we use a cantilever to transduce displacement into strain, and this strain goes into the strain gauge as resistance change. That strain gauge will be forming a part of a bridge network, and that bridge network excited with a DC voltage. That output voltage EO is amplified in a DC amplifier. Now DC amplifier, from operational amplifier we have got many DC amplifiers without any drift problem. Such an DC amplifier we can use and magnify this voltage, and finally you get a voltage output that will be calibrated by giving known displacements. That is the calibration. Here also by giving known displacement, calibrate the voltage output, and later on you may have the curve like this. This is a displacement versus voltage output of the voltage output at the end of the instrument, that is carrier frequency amplifier output voltage. So it may be coming somewhat like this. So by giving known displacement you plot it. After you plot it, later on you give unknown displacement to the cantilever end. Previously first for calibration you deform it by using a dial gauge. So dial gauge gives a known displacement. Plot this curve. Then this cantilever, at this cantilever end you give the unknown motion, and that motion you can from the voltage you can get the correct displacement. That's how the strain gauge is made use of for measurement of displacement. So this is what we learnt about regarding how to use this resistance for the purpose of displacement measurement. Next passive element is, we have already seen that resistance, inductance and capacitance can be used to transduce the displacement signal into electrical voltage. So naturally next one will be variable inductance transducer, where inductance is made use of to measure the displacement. Now the inductance is used in three forms, that is to change the self inductance of a coil, or mutual inductance between two coils, and then reluctance, that is resistance for magnetic lines to flow. Whatever the resistance, that is called reluctance. The reciprocal of reluctance is called permeance. Sometimes it is also known as permeance pickup. American firms, some of them call it as permeance pickup. So these are the three ways in which the inductance is made use of. So first we take the self inductance. It's also sometimes called inductance, simply inductance pickup, self inductance or simply inductance pickup. Inductance pickup. This is also colloquially used, inductance pickup. It means that there are, for example, there are two coils in one instrumentation of with inductance pickup. There are two coils. Each coil is a winding, yeah, on a magnetic material, and so two such coils are arranged. Your displacement xi is given to a flag. Flag is made up of magnetic material. This is a magnetic material. Magnetic material. Flag is made up of magnetic material. So when the flag is at the middle of these two coils, for example, one coil may be 8 mm diameter and say 11 mm length, typical inductance coil. So two such coils are arranged with the flag in between. When the flag is at the middle position, the inductance of these two coils will be same. So the reluctance or the impedance Z1 and Z2 both will be equal. Now these two coils are connected in the, say this is a carrier frequency bridge cum amplifier unit is nothing but carrier frequency amplifier. Carrier frequency amplifier. So it is connected. So you get the excitation. So it's somewhat like this. In the bridge network, Z1 and Z2 will form adjacent arms of a AC bridge, of an AC bridge. The other two arms can be pure resistances. So connected to the, you can connect it to the carrier frequency amplifier, and you will get the, you can get the reading here. You can get the reading of the ampli, that is output voltage. Similar, this it is similar to the signal flow diagram. Yeah, instead of cantilever, you can say flag is used, and then the inductive pickups. Say displacement we give to a flag in terms of this. We call it, this is, you call it AC bridge. All the things, all other things will remain same as it is in AC carrier frequency amplifier. So this is one form of using the self inductance pickup. That is, when the flag is at the middle, the inductance of these both the coils will be same. When the flag moves nearer to, say, coil 1, then inductance of coil 1 is more, and to the same extent the inductance in coil 2 is reduced. So it's opposite effects. When the flag moves, in one coil increase, in the other coil decrease to the same extent. Hence opposite effects are connected in adjacent arms of a bridge network, what you have learnt already under bridge network. So this is a flag type. Another type is, we can use a core. The flag itself may be made in terms of core, and it is positioned at the middle of a hollow cylindrical inductive coil. That is, it is made up of one coil and with a center tapping. With the center tapping you find, then from center tapping to one end we have got one coil Z1 with the impedance Z1. Then from the middle point to the other end of the coil we have got the coil equivalent to coil 2 and with the impedance of Z2. So now when the magnetic core is at the middle, we find magnetic material distributed equally to both the coils. So impedance Z1 and Z2 will be same, and if we move coil by giving Xi displacement, Xi is the input signal, same as displacement, because it's a transducer for measuring displacement. So when you give the displacement here, suppose we move from left to right to some small x, of course the displacement is limited within this length of the total coil. So if we slightly move, what will happen? Then inductance in coil 2 will be more than the inductance, that is, the inductance in coil 2 is increased and to the same extent it is reduced in the coil 1. So it is similar effect, but here we have a core moving inside a hollow cylindrical constructions. So physical construction is different here. Instead of two separate coils, it is made in hollow cylindrical construction, and you have a core. So with this again Z1 and Z2 opposite effects for a given motion, they are connected in adjacent arms, and then other two arms can be resistances. So again we connect to AC supply and take output. This output actually is given to, will form part of the carrier frequency amplifier. The second way of using the inductance pickup is mutual inductance. We have seen earlier the self inductance, now mutual inductance, and it has got a specific name. Such transducers, one such famous name is LVDT, linear variable differential transformer. So it is very well known in measurements. People simply call LVDT. The construction details are shown here in the figure here. So we have got this is a magnetic core made up of magnetic material, a core made up of magnetic material. We will simply call magnetic core. So it is positioned at the middle. The construction is same as more or less similar to our self inductance with the core. Here also you will have a hollow cylinder, but here you have 3 coils, one primary coil and 2 secondary coils. In earlier we have only one coil with the central tapping, that is inside you have the difference of constructions. So primary coil is excited by an AC voltage which may be varying 5 kilohertz to 20 kilohertz. It is decided by the frequency of the input signal. Now input signal is here, it is given to the core, that is the displacement. Input signal is given to the core, to this extension rod. At the extension rod, whatever the displacement we want to measure, we give it to the rod, so the core will be moving. So now assuming the core is at the middle, now we find the mutual inductance between primary coil and secondary coils are when it is middle, they are same, that is mutual inductance here, inductance between this primary coil and secondary coil 1 we call mutual inductance M1, and similarly the mutual inductance between the primary coil and coil 2 we call M2, mutual inductance 2. So proportional to mutual inductance, voltage is developed here. That voltage, suppose we call it as EO1 is equal to M1 times DIP, that is current flow in, that is IP, current flow in primary coil, by dt. The rate of current flow into M1 will give the voltage developed in the secondary coil 1. Similarly, S2 is equal to EO2, that is voltage developed in the secondary coil 2 is equal to mutual inductance M2 into DIP by dt. Now these 2 coils, as we see, they are connected in opposition, polarity opposition. So we find the net voltage appearing between these 2 coils is the difference between these 2 voltages. So EO is equal to EO1 minus EO2 is equal to DIP by dt into M1 minus M2. This is the voltage developed at the terminal of the secondary coils. The terminals connecting secondary coils output voltage is proportional to this. Now when we change the displacement, suppose the D is 0, that is the core is at the middle, then you will find M1 is equal to M2, and M1 is equal to M2, EO is 0, EO is 0. Now when we give a displacement, suppose we move this core towards S1, suppose we move in this direction, then you will find mutual inductance M1 is more and M2 is small, so you will find EO1 is larger than EO2. That difference between these 2 things will appear. Suppose ES is of this nature, then EO1, so EO when Xi is positive. Suppose you call this as positive this direction, or we can also assume as per the diagram, let us assume here, and yeah, it does not matter, we can have it same direction. So if this is positive, if we define the towards left is positive, then you will find the SO1 will be somewhat like this. If voltage developed EO will be somewhat in phase with the supply voltage. Suppose we move the other side from the other side towards right, then if it is from neutral position, it is a negative moment, considering the left hand motion as positive. This is a negative motion, and you will find in this case S2, mutual inductance between primary coil and S2 is more. So you will find voltage developed in EO2 is larger, EO2 will be larger than EO1, then you will have the 180 degree phase shift, that is this way. When Xi is negative, then you will find the output voltage will be opposite, that is 180 degree phase shift will be there. That is what is shown at this point, you will have 180 degree phase shift. That is the RMS value of EO if we consider, you will find when Xi increase positive, the output voltage is increasing EO, and with 180 degree phase shift it also increases the other directions. That is when Xi is negative, this is Xi is negative and it is moving in this direction. Suppose we withdraw it completely, you find then nonlinearity starts. So within the dimensions of the pickup only you are supposed to move the core. That is why it is called a linear range for the operation. So that is how the LV, linear variable differential transformer construction is there and it's functioning. But if you see the signal flow diagram, you can see the Xi when it is that is displacement given to the core, and it is given to the core of the LVDT, and we have the excitation voltage that is for the primary coil. We have the excitation voltage that is taken from the oscillator, which may supply any voltage from any frequency between 5 and 20 kilohertz, and this is decided depending upon the input signal frequency. The carrier frequency, the oscillator frequency should be at least 10 times the maximum frequency of the input signal, the frequency with which we are going to change the input signal. So depending upon that we can select the frequency in the oscillator. So that signal is given to primary, and the output voltage EO will be the frequency of this, I mean magnitude of the input signal is superimposed over the carrier signal, and you got so called modulated voltage is obtained as the output from the secondary coils. Suppose the motion is only on one side of the neutral positions. Suppose the motion is only at the right hand side of this neutral position, then we need not have this sophisticated instrumentation, that is phase sensitive demodulator, filter and all is not required, because the average value of the modulated signal alone can be read in a AC voltmeter. Yeah? In AC voltmeter, that will give the RMS value that is proportional to the displacement what we have given. But suppose motion takes place on both sides of the neutral position, that is it moves to and fro like this. What is given is positive motion, positive side, that is this side it motion, and the other side also it goes. Then you will find if you use only AC voltmeter, the direction will not be known. In such cases we take the EO and give it to phase sensitive demodulator, where again with a synchronous signal from oscillator it brings these waves to the same side of the signal, and after low pass filter you get a voltage output proportional to the displacement what you have given, and that can be calibrated in terms of known distances, and unknown distances can be read from the meter. So that is signal flow diagram of a LVDT. We have to note here, important point is, in instrumentation for LVDT there is no bridge network, only for inductive pickup there is bridge network, and LVDT we need one more point, we don't have even the amplifier, because if it is sufficient magnitude we can simply without amplifier we can get few volts, 2 or 3 volts that can be calibrated in terms of displacements. So there is no amplifier in some instances. If you want you can add amplifier here also, if this small hole you can add, but that's not a must, and main point is there is no bridge network in the instrumentation for the LVDT. So this is for linear motion, yeah, along a line. Xi is that is displacement along a line. When it is in the suppose it is pivoted, you can give the motion rotary motion also. Hence it is called rotary variable differential transformer. We give this angular rotation to this again magnetic core, same construction made along an arc. So this is primary coil P, this is S1, this is S2, same way it functions. But here the displacement, the angular rotation is given to the LVDT, hence it is called rotary variable. Otherwise the functioning is same principle as that one. So that is regarding the mutual inductance. Now the reluctance variations, reluctance variations, that is third way of using variation. Third way of using the inductance is you change the resistance for the magnetic line to the flow of magnetic lines. That is what is achieved in microsyn. The specific name here is microsyn, or it is sometimes it is called proximity pickup in some other construction, that is second construction. So the reluctance variations is achieved by this, like this. So there is a rotor which can make a rotation theta, that is our input signal Xi. Yeah. When it rotates we find the resistance for the magnetic lines, for one line is shown, 1 or 2 lines are shown here. So the magnetic lines are induced on the poles 1, 2, 3, 4 poles are there in the stator, and there is excitation coil. This is your excitation winding. This is excitation. Excitation winding is shown here as a yellow line, and each pole has got excitation winding as well as the secondary winding. So the excitation winding is similar to our primary coil in the LVDT, and the secondary winding as it is shown there is shown here by say green line. So each pole has got excitation coil and the secondary coil. So because the excitation coil, the magnetic lines are induced, and that path is shown here. So that is, now if suppose the rotor is in the neutral position, then you will find rotor material that is shown here. This is rotor material is distributed equally to each among all the 4 poles. Half of each pole is covered by the rotor material. Rotor material is made up of again magnetic material. It's made up of magnetic material. So magnetic material equally distributed among the 4 poles. So number of lines produced because of this you find the reluctance of each against each pole is also same in the neutral position. So the number of lines in each pole is same. So north pole is here, north pole, north pole, south pole, south pole. So you will find 2 lines, probably 2 lines here, 2 lines there, and 2 lines entering here, 2 lines entering here. So you will find the number of lines entering or coming out of each pole will be same for the neutral position of the rotor. Suppose it rotates to a small angle. Now normally here theta is varied plus or minus say 15 degrees. Only small angle rotation is possible to convert that into displacement signal into rotary rotation of plus or minus 15 degrees can be converted into an equivalent voltage here. So if suppose we rotate towards say anti-clockwise, suppose we rotate anti-clockwise through say few degrees, say 5 degrees, then you will find material comes here more, that is poles 1 and 3 you will have more material, and here it will withdraw. So you will have 2 and 4 you have less material. That means the more number of lines are there in pole 1 and 3 and less number of line in 2 and 4. Now the secondary coils are wound in such a way, the coils 1 and 3 they add each other, and 2 and 4 the 2 and 4 also in connect in series, but in combination it will oppose 1 and 3 voltage. That is similar to our secondary coil. So one coil is made up of the winding 1 and 3. The second primary secondary coil will be made up of the 2 and 4, and they will be the voltage developed in these secondary coils will oppose each other. So when they are connected in series, all of them, then you will find 2 adding, 2 subtracting, net voltage is is appearing here. So you find that is 1 and 3 voltage is increase, and 2 and 3, because whenever they change in when there is change in magnetic lines and they interact with the secondary coil, they induce voltage. That's how the voltage is induced in the secondary coils. And 1 and 3 they aid each other, 2 and 4 aid each other, but in opposite to the polarity of 1 and 3. So net voltage is coming here as it is in LVDT. But what you have made use of is the reluctance. Since more magnetic path, more magnetic material is brought, reluctance reduced in 1 and 3. At the same time, reluctance is increased in 2 and 4. So it is opposite effect producing 1 pair. Increase 1 pair, and the other pair of poles the reluctance is increased. That is what is made use of here to convert that rotary motion into voltage. So this again you can as per the signal flow diagram as LVDT, we can give this is a modulated signal. You can amplify it if you want, or you can give it a phase sensitive demodulator and then low pass filter, same instrumentation, low pass filter, and then finally you have the voltage output. Yeah, that part of it I have not shown. This is one way of using the reluctance variation. Another one is simply called proximity pickup. Yeah, it's well known. And the construction is you have got a north pole, south pole, a magnet, permanent magnet, on which there is a coil wound over. And suppose a gear is just below or in the vicinity of this device, at one instant say a tooth comes just behind just below the this arrangement, then you will find this is this made up of magnetic material. Yeah, this is made up of magnetic material again, magnetic material. So you will find the since presence of magnetic material induces more magnetic lines in this. So let us have the north pole here, this south pole. So more magnetic lines will be coming out of the north pole in the presence of a magnetic material. And as it rotates, immediately you will find a valley. Then reluctance is increased. The number of lines will decrease. So that means when a tooth and valley passes in front of this permanent magnet, you find number of lines changes. When the number of lines changes, then you will find that is cutting the number of the coils will induce a voltage here. So whenever a tooth comes out, you find one pulse is produced. That's how you get a pulse output from the proximity pickup. Proximity pickup is made up of a permanent magnet on which we have got a coil. So in the coil you have the voltage induced, and if so 100 number of 100 teeth are there, then in one rotation you have the 100 pulses. It can be read in an electronic voltmeter and electronic counter, and you can divide by 100 means you may have so many rotations. That is how the reluctance made use of here to in measuring the rotary motions of the any magnetic material. Yeah. Now we see the third element. We have seen the resistance, inductance, how they are made use of for a displacement transducer. Now we see how the capacitance made use of to transduce a displacement into a voltage. Now we know in a capacitance normally we go for the parallel plate type of capacitors. So having two parallel plates, having a distance of d, and say a distance this is distance in millimeter, and the area is millimeter square. Then the capacitance, assuming dielectric constant, dielectric medium, say air is equal to 1.006 something like that for air. So some dielectric medium is there. So the capacitance of such a parallel plate capacitor is given by this expression 0.0086 epsilon dielectric constant. Area is the common area between the two plates, and d being the distance in millimeter and millimeter square respectively. That means capacitance is depending upon three parameters: dielectric medium, plate area, and the distance between the plates. So if we can give the displacement to vary any one of these parameters, then capacitance will vary. That is the principle what is made use of in these three types of capacitors. Because same displacement you can give it to in three ways. This is the option available for the designer when he wants to design a capacitance transducer for to convert the distance into voltage. He can have any one of these three designs. For example, here the distance d is varied by having one plate fixed and giving the displacement to the other plate xi input signal as displacement v gives. Then d is varied. When d is varied, and inversely you have got the variation in the capacitance, and the capacitance will be made into some circuit which you will see little later. The other way of using the d is you have some dielectric medium, some mica or some material, insulating material. They are good dielectric materials. So some mica is there, and it is put to some initial position like that. You can move either this way or the other way. Then you will find the actual in this position half of the volume is made up of air, other volume is made up of mica. So when you move it, then the moves towards say left, then the air medium is reduced and mica is more, and you will find the epsilon is increased. So similarly you will find when you give different displacement, epsilon is varied, and epsilon is varied, proportionately capacitance is varied. So similarly here we find the common area. Suppose this is the normal middle position, that is this point is just middle of this other plate. Then you can move the one way is you can call it positive, the other direction is negative. So it will produce the opposite effects. Suppose if you move here, A will be increased, the capacitance is increased. You move the other side, then capacitance reduced since A is reduced. So from the middle position we can increase or decrease, and accordingly the distance from 0, either positive side, negative side, you can make use of. So these are three ways, either varying the distance between the plates or varying the dielectric constants or varying the common area. We can convert the distance into capacitance. Now how capacitance is made use of in a circuit to get a voltage, that is explained in this simple circuit. The capacitor, parallel plate capacitor is forming one of the elements in the circuit with resistance. So this is your supply voltage EB. And now it is for deriving an expression, it is assumed like this: at any instant let the distance between the two plates be x, and we are giving the distance input signal to this other plate, bottom plate. Now when xi is 0, let us call x as x0. Yeah. So at any instance x is equal to xi plus x0. At any instant x0 is the when when we don't give any input signal xi, so that is xo. So xo plus xi will be at any time x, or you can write xi is equal to x minus xo. And we can derive an expression if EO is the voltage drop across the resistance R, then we can EO is the output voltage, that is EO, voltage drop across R is our output voltage EO, and EO and xi, the plate displacement xi input signal. Under these definitions we can derive this equation in electrical technology, where k, I mean k tau d by the time constant tau 1 plus tau d, where k is equal to EB minus, that is excitation voltage, that circuit supply voltage divided by the xo. When xi is 0, whatever the distance is xo, that is volt per millimeter you will have. Then xi already we have seen. Tau is equal to time constant co, that is this will have its capacitance when x is or xo or xi is equal to 0. Co into R will give the time constant for the circuit. So in that terms we have got this relation. And when you want to find out the frequency response of this equation, normally what we do is substitute the differential operator d by I omega. So by substituting by I omega, you have got this equation, which gives rise to magnitude ratio and the phase angle like this. This you can reduce this to this form, and that is when omega is equal to 0, this is 0, EO by A is k. That is when omega is equal to 0, then you find EO by xi magnitude, that is I omega will be k. That is magnitude ratio of EO to xi will be k. That is 0 when it is 0. When it is 0, this is when omega is 0, this becomes infinity. Then when it becomes infinity, then you will find k by infinity will be 0. That is why you have got 0 voltage. Suppose omega is infinity, then this term will become 0. Then you will find EO by xi will be same as k. That is how when omega becomes infinity, the curve approaches the value of k. That is how the magnitude EO varies with reference to omega. Similarly, you will find when omega is 0, it is phi will be pi by, that is this infinity, 10 minus to infinity, that phi will be tan phi, tan 90 is infinity. So you have got 90 degrees, 10 pi by 2 infinity. So when omega is equal to infinity, this will be 0, then tan 0, it becomes 0. So that is how the angle is varying. Now that means when omega is very large, then only that EO is proportional, k means EO is proportional to k. Suppose EO by xi is equal to k, that means it's a constant, and you will find k into xi, taking that side. So output voltage is proportional to k, is proportional to xi only when omega is larger than, say, omega minimum, assuming a 5% error. So this, if you say 0.95 times k, 5% error in this instrumentation, then you will find assuming making this side will become 0.94, 5% error, this side will become 0.95. Then you will find omega minimum, that is we can also write EO by k, that is making it into 1. You can also write this as 1, bringing EO by k by xi I omega, and making it for 5% error, the ratio will be 0.95. Then you have got omega minimum. Omega minimum is equal to 3.04 by tau. So if substitute in this equation, then omega minimum you get as 3.04 over tau. So, for higher value of omega being more than omega minimum, then you will find the error is always less than 5% or it will more than 0.95 the magnitude ratio. In order to have omega minimum as small as possible, what is the requirement? Tau should be larger. To make omega minimum smaller, so that if even we can use this instrumentation for smaller frequency of what is omega? Omega is the frequency at which we vary the input signal, that is the input signal variation frequency is omega. So, if we have lesser omega minimum, then even at lower frequency we can measure it. Also we have to note when omega is 0, that is static measurement. When we just move it and keep it there, that is no omega, omega is 0, no frequency. That is under static measurement we see output voltage is 0. So, the simple circuit with capacitor you cannot use it for static measurements. So, only for dynamic measurements, and dynamic frequency should be more than 3.04 over tau for 5% error. If you vary the percentage error, then accordingly you can find out. Suppose 2% error means you put 0.98, 2% error. If you allow only 1%, 0.99. For that what is the omega minimum you can find out. But 5% error is normally allowed. So, having 5% error, omega minimum so much. So, in order to reduce, in order to have a as small value for omega minimum as possible, then you should have the as large tau as possible. Now, what is tau? Tau is equal to CO times R. That is capacitance at X is 0 and other one is R. So, normally having larger R, we can reduce omega minimum. So, R is of the order of some mega ohm, 1 or 2 mega ohm. The problem here is we have reduced omega minimum, but the voltmeter which we bring to read this voltage will have 10 times this. So, it should be 10 omega, 10 mega ohm should be the resistance of the voltmeter. So, that is how it is a high impedance circuit. To convert it, we go for the impedance transforming amplifier. So, by that we convert this high impedance circuit into low impedance circuit, and later on you can connect a voltmeter. That is usage of the impedance transforming circuit. In the transducers using capacitance and piezoelectric transducers, we make use of the impedance transform amplifier like that. So, the simple circuit with one capacitor has got this drawback, it cannot be used for static measurement. If you want to use the capacitor for the static measurement, then we go for the bridge circuits with the capacitors, AC bridge circuits with the capacitors. That such 3 constructions are shown here in this figure. That is, capacitance is varied by varying the distance between the two plates of the parallel plate capacitor, or by changing the epsilon, that is the dielectric constants, or by varying the area. This is area variation, here it is epsilon variation, here it is d variation, distance variations. But they are connected in adjacent arms of the Wheatstone bridge. This is a Wheatstone, this is AC bridge, it is drawn in a diamond construction, it is a different way it is drawn. Across 2 corners you find the output voltage, the other 2 corners you give excitation. Same circuit in different way it is drawn. Whenever we give a displacement, suppose we give the displacement here xi, then we will find the distance here is reduced, the distance the other capacitor C1 is increased, accordingly the capacitance varied, and for the change in capacitance you will have the one given output voltage. Similarly here we find the dielectric medium, say mica, is moved from this middle position this way or that way, accordingly the epsilon is varied, correspondingly the varied in adjacent terms, they are connected in adjacent. For any given variation, the variation in C1 C2 will be opposite in nature. Similarly, by having a cylindrical construction for the plate, this is cylinder 1, cylinder 2, and this is a rod having a common area equal in both now to start with. Later on, if you move right hand side, C2 will increase area, C1 will reduce. So, they are connected again as adjacent terms of a AC bridge with the excitation and so forth. So, the output voltage we know it is a modulated one, we can amplify it, and then phase sensitive demodulator, low pass filter, all these things are understood. These things I am not doing it. It is by using carry frequency amplifier we can read the output voltage corresponding to this. So, this one construction. Another construction where static signal can be studied is a capacitant with operational amplifier. Yeah, we have got 2 capacitance. One is in the forward line, other is feedback path C2 capacitor. And now suppose ES is the supply voltage, then EO is equal to EO of this EO is given by EO is equal to C minus C1 by C2 ES, that is EO, the output voltage of this setup, that is operational amplifier with a feedback capacitor, and then it is going to phase sense demodulator, low pass filter, finally you get the output voltage. The output voltage is varied depending upon the variation in C1 and C2. You can select the variations, either you can put the variation in C1 or C2, because you find this Z2 by, actually EO is equal to Z2 by Z1, Z2 by Z1. This is giving rise to the impedance of Z2, this impedance of Z1. Now we know impedance is equal to 1 over C omega, this is our impedance, impedance of capacitor C is equal to Z by 1 by C omega. So now since it is inversely proportionate, you will find minus C1 by C2 ES, because Z1 is inversely proportional to C1, so it goes up. Now we know each one is made up of these 3 parameters. This is equal to C1 is equal to epsilon is proportionate to epsilon 1 A1 by D1, and similarly C2 you got epsilon 2 A2 D2. Yeah, because capacitance is epsilon proportional to area into dielectric constant divided by the distance. So converting that in terms of parameters. Now if we have the area change you give, because we want EO proportionate to proportional quantity, then we give area as well as the dielectric constant variation in capacitor 1. This capacitor 1, we want to vary area to change the capacitance, then give it to capacitance 1. And when we want to give the distance as input signal to vary the capacitance, then that distance give it to capacitance 2. That D2 comes up at the top, so you will find EO is proportional to D2. So we can give the signal in form of displacement between the plates, or the common area between the plates, or the dielectric constant. For that we can select any one of these 2 capacitors. That is for area and dielectric constant capacitor 1, distance we give to capacitance 2, then you will have EO always proportionate to our displacement signal. So that is what is demonstrated by this equation. That means we have seen all the 3 passive elements, resistance, inductance and capacitance, how they are made use of to transduce a displacement into a corresponding voltage.